ASIC methodology provides multi-million gate designs with 90 nanometer semiconductor technology solutions and system-on-chip development.
The main objective is to build a CPU architecture based on an ASIC device, application-specific integrated circuit device, or based on an FPGA application. Also, an important segment of the CPU infrastructure is the control unit. The control unit follows the stored list of instructions directing the activities of the arithmetic unit, the I/O devices, until the program has run to completion. Each unit performs its task under the synchronizing influence of the control unit. An important segment of the CPU architecture is the arithmetic logic unit, which are combinational or sequential logic circuits to perform operations on data as instructed by the control unit. Each arithmetic logic unit is characterized by the type of data that it can manipulate and the test of operations that it can perform on the data. The ALU supports operations on integers of different sizes and may also include operations to manipulate the fixed point and floating point numbers and various numeric data. Such specifications are part of the arithmetic add, subtract, multiply, divide, logical and or and exclusive, shift and rotate data, convert data from one type to another. In this design, the memory hierarchy is well defined. The high speed of hits and misses is important. For instance, hit time is the time to access the upper level of memory hierarchy, which includes the time to determine whether the access is a hit or a miss. Miss penalty is the time to replace a block in the upper level with the corresponding block from the lower level, plus the time to deliver this block to the requesting device, normally the CPU. The miss penalty is further divided into two components: access time, the time to access the first word of a block on a miss, and transfer time, the additional time to transfer the remaining words in the block. Access time is related to the latency of the lower level memory, while transferring time is related to the bandwidth between the lower level and upper level memories. Sometimes access latency is used to mean access time. The memory address is divided into pieces that access each part of the hierarchy. The block frame address is the higher order of the address that identifies a block at the level of the hierarchy. CPU clock cycles to recover from an I/O activity, such as cache flush, list the memory and I/O bus resource demands of each I/O device, even when the CPU is not using memory. The bandwidth of main memory and the I/O bus are limited. The final step is establishing performance of the different ways to organize these I/O devices. Performance can only be properly evaluated with simulation, though it may be estimated using queuing theory. Defining the processor data path. It consists of execution units such as arithmetic logic unit and shifters, the registers, the communication paths between them. The data path contains most of the state of the processor, the information that must be saved for a program to be suspended and then restored for execution to continue. In addition to the user-visible general-purpose registers, the state includes the program counter, the interrupt address register, and the program status register. The latter contains all the status flags for the machine, for the CPU, such as interrupts enable, condition codes, etc. In designing an I/O system, analyze performance, cost, and capacity using varying I/O connection schemes and different numbers of I/O devices of each type. I have concluded part 1 of the ASIC/FPGA CPU design. Part 2 of this design will be available very soon.